Hello viewers and welcome to another episode of Space Science with Python. In our last episode we talked about the new upcoming machine learning project about asteroid spectra, and I uploaded the script from last time with some more information on my GitHub repository. The link is in the description. So here, just as a reminder, last time we were just fetching the data, so downloading the data from the repositories. I added also some references regarding this reflectance spectra. We talked a little bit about reflectance spectra as well, and checked whether everything has been downloaded. Now, all the data that we are using and also the machine learning stuff will be developed and deployed on Google Colab. So you don't need to install anything. Of course, the code can also run on your local machine with the requirements.txt that you find in this repository. But I made it a little bit easier now. So you see here on the very top a small badge which says open in Colab. And if we click on it, we see that the script is directly loaded into the Google Colab environment. If you execute it, it will also warn you that that the script is not something that you wrote, it's from GitHub, so are you sure you want to execute it, and so on. It will also ask you later here that it needs access to the Google Drive, where we want to download all our data. So let's maybe just execute it quickly, run all. So now it's warning us, it's not authored by Google, but run anyway. I mean, you can go to the code and see that it's there are no nasty code snippets in there. Now it's trying to initialize some environment. Here on the right side, it says it's busy, or it was already initializing. Now it's busy. Let's wait a few seconds. It will also ask me in a few moments about the Google Drive access. It takes a little bit longer than usual. Now this is some kind of presentation effect, I guess, but let's keep it running because I already executed it and I don't have all the data here in the repository. So Colab, Asteroid Taxonomy data, and there we have the different level folders, or starting with level 0, the pure raw data that have been downloaded. So the bus taxonomy txt and the tar file, and also the unzipped file with all the files in here. Now, before we do some more data cleaning and parsing, this looks not good. Let me interrupt the execution, and yeah, now it's executing. Okay, this is now. Okay, now it was a keyboard interrupt. Well, this happens in this kind of tutorials. Nothing runs smoothly and perfectly as always. But anyway, you see I have already the data here. And we will go a little bit through the data, or understand a little bit, before we are doing some more data parsing. So we are combining two datasets today that will be later used, or in the next session, for feature engineering and also understanding the spectra data itself. So if you recall from last time, we were talking a little bit about reflectance spectra. So the sun is shining, it shines on some asteroids. The asteroid reflects the light, but only not like a mirror, but yeah, depending on the wavelength, so the color of the light, the light is reflected with different with a different reflectance. So at the end of the day, some asteroids appear redder than others, or bluer. Some have some kind of broader absorption lines, and so on. And based on these different reflectance spectra, we have a classification schema that you find in this txt file that we downloaded. So first of all, we see here the different asteroids from this survey we were discussing last time, with around 1,400 asteroids like Ceres, Pallas, Juno, Vesta, and so on. Now in our second column, we have the so-called Tholen classification from a work in the end of the 80s with classification numbers or letters like G, B, S, V, and so on. And then the SMAS2 classification with the PhD thesis or in the publications I referred last time, that was published 1999 with these new classification like C, B, S, K, V, and so on. So not in this one. In the future videos, we will talk more about these designation numbers. We will talk a little bit more how what kind of different classification schemas are there. So for example, Tolen and SMAS2 are just two classification schemas, but they are way more. But let me say one thing. There's a lot of helpful content. Of course, I can refer to the PhD thesis and make my life easy. I can refer to some Wikipedia articles and make my life even more easier. But yeah, there are like 4 major groups you have to know. The one is the S-type comet, or asteroids. So which is like, let's say stony, or as you see here in the top, with some mineralogical composition. We have also so-called C-type asteroids that are have carbonous properties, and they have some subgroups. So for example, here in this article you see the C group with the SMAS subclassification. The B-type corresponds to some other types. We have here the CH type with an absorption feature at around 0.7 micrometers, so around 700 nanometers. So you see there are some small or some deviations in this reflectance spectra where this classification schema is based on. Now for today's video and for the data fetching and merging a little bit, data crunching, it's not really necessary now to understand all the scientific background of this reflectance spectra. Don't worry, we will get to there. Of course, if you start a machine learning project, you have to first understand the science and then doing the data. But here we do it a little bit more. We're switching between these topics because, well, I'm guiding you a little bit through this topic. And so it's not necessary for now to understand fully what's going on, but we will get to there in a future video before we start our machine learning part. So now we are still in this data engineering section. So we have also here now the SMAS2 data. We see here some strange files with .2 and spfit.2, some weird numbers and a lot of them. And these numbers here, these designation numbers, they correspond to the file that I showed you before, this txt file, with the classification based on Tolen or SMAS. So we have to link these files with the classification. So the goal today should be a single file with all information that is later necessary for feature engineering, for visualizing the data, and also for machine learning itself. But let's take a look at one of these files. So I just downloaded one, and this is the content. It's plain and simple. What do we have here? We have here in the first column, we have the wavelength of the asteroid. So the reflectance at a particular wavelength. 0.44 means 0.44 micrometers or 440 nanometers. So this is like, let's say, very blue, or I would say, is it even already ultraviolet? Could be. Violet light. And there we have a reflectance value of 0.281. So what does it mean? Well, let's go a little bit through this data set here. This data, the reflectance of the wavelengths, they are normalized at 550 nanometers. So all 550 nanometer entries in all these files have the value 1. So, and the reflectance spectra are normalized based on these 550 nanometers. So high reflectance or lower, a higher reflectance or lower reflectance with respect to 550 nanometers. Now this file here has a resolution of around, or is provided in 10 nanometer steps from 440 nanometers to 920. And this applies for all the data. So the data itself is quite clean. It's already normalized and everything. Whether this normalization makes sense for our machine learning algorithm needs to be determined. And of course, with these numbers, we cannot see a lot. We have to plot it to get a feeling and understanding what is the difference between S and C class and so on. And when we visualize it, we can talk also about the scientific background of these files. Anyway, I would suggest today to just simply merge these data a little bit, do some data cleaning so that we have a single file, a level 1 file, so a derived product that can be used later. Well, I will provide also this S-type and C-type links in the description as well. Now I have here a new Google Colab notebook. Let's call it 2 minus data parse, data parsing, data parse. And I already executed here the libraries and also the access to the Google Drive. Now I would like to merge all the data and we have to take a look what this data is all about. So I would suggest to first get the file paths that are in Google Drive. So let's use glob and glob and use OAuth path join. We use the core path, whether you're working locally or in Google Drive doesn't matter. This should work out of the box. Level 0 and all the spectra parts, they are called something like S or are an S mass 2 / star sp fit star. Let's execute it and we can take a look. I don't know what's going on today. It's quite slow. Strange. When I cancel it, it's okay. Anyway, here you see all the files, all the spectra reflectance files that that are available. And I just showed you a few seconds ago one of these files. Now this is a little bit huge, so let's delete this cell here and let's create a new cell where we have to be careful a little bit, because I know, of course, already the numbers, but if you take, for example, the first 10 files, you see here the number, A00001 and 2 and 3 and so on. But let's take a look at the last 8 ones. We see here that we have some kind of designation numbers. So AU 1995, WQ5 and so on. These asteroids probably have already a name or some other number, but at that point they didn't. So we have to be careful and separate our file paths by designation files and the non-designation files. Let's call it like this. So let's do it quite simple. It's until the last 8, and then let's call it, I don't know, non-file paths. Well, this is a little bit confusing, the name, but then they have equal length. So let's separate them first. And then we can also create a pandas data frame with these names to handle the data maybe a little bit better. Data frame equals this one, and then we call the column something like file path, I would say. File path, and then the other one is then correspondingly the non-file paths here, and that should do it. Okay, perfect. Now we want to add the designation, or let's call it non-designation number, as a column in our data frame. So we want to, because we have to link this taxonomy file with the G and S numbers, letters, with this files, with the spectra files. So we have, based on, we need to take the file name, the designation number of this file name, and link it with the taxonomy files from this txt you just saw. And of course, I just played around a little bit previously, so this is not too difficult. We just need the file path, and we need to apply a function lambda x, and we take the int, so it's like it's an integer value. There are no letters in there, and we have to search for these asmas2 /a, so regular expressions where we search for the numbers after the letter a. You may recall it was just a and then some numbers. spfit on x, and then we have to take the result with the group. Group 1. So let's see what this will provide us, but maybe I should also do it for the non. Wow, this is really a bad name, but yeah, let's stick to this. I just made the decision. So here is non, here is non, and I have to be careful because here it's not an integer, it will be a string. So let's do this and let's take a look at the very first 5 rows. So this is like the designation number for the number 1. So maybe I should just, I don't see it here, but when I hover over it, maybe. Nope. But let's take the file path and then ilog 0. So it's here, yeah, it's just the number 1. So that's why the column was also, had the number 1 there. And for the other one, we have probably some, here we have some, the designation, but I see there's still the U in there. So yeah, it was a U. So now it should be simply the name of the asteroids. Yep, there we are. 1998 BM2. Yeah, some kind of asteroid. Just take a look what this is. I don't know. Cool. Okay, so let's delete this cell here. So now it's time to link our spectra or with the taxonomy. So my suggestion is now let's read in first the taxonomy class. Let's call it asteroid class df. Where I just see read CSV, and I have to say it was a little bit a pain to read this file. It was not really. I wouldn't say it's still trivial. It's just a CSV file, but you saw. If you maybe remember, it just wasn't a plain column file. There was some meta information on top and so on, some fancy heading. So I have to play around a little bit here. Taxonomy.txt. And we have to skip some rows because of this header. And the skip rows was 21. And the separator was not white spaces. The separator is, I love it, tabulator. I don't like this. And then we have to define some names. So the first one is the name of the asteroid. The second will be the Tolen class. So let's call it simply Tolen_class. Then we have the bus class or bus class. And then the funny thing is that we have some columns that are just empty. So I just call them unknown 1 and unknown 2. I don't know what's going on there. So let's have a look at the taxonomy data frame. And there we are. We have the name, the Tolen class, the bus class, and surprisingly empty columns. Yeah, I don't know. I think if I remove this, there will be some error being spawned. Ah, no. Surprising. No, this is really surprising and awkward for me, but somehow, that's strange because locally I had an error there. Now, in Colab I don't have. Should have tested this in Colab before. I will just stick it now just to be really careful. But yeah, try it out locally. Let me know if it also works without these unknown 1 and unknown 2, because for me somehow it doesn't, but yeah, I don't know. Okay, so this is our data frame. And now we can, yeah, first of all, we have to strip the name. So we have here the number 1 and series and so on. So we need to take the numbers later. So first let's simply remove the white spaces here in between. You see also here 1998 WS, there was no, in our file name of the spectra, there are no white spaces. So simply remove the white spaces. Let's call it here simply no name equals to this one. Name, apply lambda x strip, and then copy. Now we need to separate also between the designation numbers and non-designation numbers, as I just said. You see here we have here number 1, 2, 3, and so on, and here we have these, the last 8 ones of the txt file have this strings. So let's take our other class here. We just define the designation class, and yeah, as similar as before, we then first of 1403 have the numbers, and the last ones they don't. Non-asteroid class. Yeah, this is no good wording. Okay, let's execute it and let's verify this with this non-class thingy. Yep, there we are with some numbers. And you see here we have way more asteroid names than spectra. Well, yeah, we don't have data for all, don't have all the spectra. There are some parts missing. So if we make an inner join, some parts will be left out. Okay, so let's maybe create a designation number for our first data frame. So we take the name and then say apply lambda x and split, then taking 0. So let's see how this looks now. Just some quick and dirty coding. And we have here our designation number now. So this works. All right. But strangely, it was not 100% correct with the separation. I still see some files here. Okay, after some confusion about my own coding and so on, it's actually quite clear, or what I mean with quite clear. It is now clearer for me. So we removed all the white spaces all around the names. And now we just taking the numbers, the designation numbers. And I saw here we have 1 series, 2 Pallas, and so on. But we have here asteroids, which have the name like 1991 PE10, and then a number, a previous, or probably a preliminary number that is probably now being removed already. This is just my speculation why I was confused. And this is a thought that I forgot while making this video. So if I just take this non-asteroid class DF, there you see the very first entry, yeah, starts with simply the year and not with any number before. So, okay, it's more clear for me. naming conventions and so on in astronomy are extremely confusing. You see, I'm still affected by all this confusion. So yeah, just wanted to be brutally honest that, yeah, I also get sometimes really confused with all these designations. But yeah, that's live. Okay, I think I restored my honor a little bit. Now let's merge our data frame here with the taxonomy. So we are doing simply a merge, where we say we merge the classification with the file paths df, designation file paths df, and we make this on the designation number. So let's see whether this worked or not. And we see here we have series, we have the designation number. This is the key that is then being used to join with our files. And here are the file paths to the corresponding spectra. This appears to be working. Perfect. The same thing applies also for our non-designation asteroids. So just write down non_asteroid class df.log. First of all, we have to determine the designation name. Number, I mean, not name. And then we say asteroid class _df. Take the name. And then apply lambda x dot replace the empty spaces between the letters and the numbers and so on with blank, with nothing. And then it's asteroid class df, or no, asteroid class join df equals non-asteroid class df. We have now in line 1, and we will merge this with the file paths name, so non-file paths df. And the key we want to join on is, of course, designation number as well. So let's take this one here. We have 8 rows, hopefully. Yeah, 8 rows, the name with the designation number. Now here's not really a designation number, just remove the white space. But this one here corresponds with the file name in our spectra files we have in the SMAS directory. Perfect. Now we can now merge our final data sets now. So let's call it simply asteroids df. So we used a new function called pandas concat, so concatenate. Both files have the same structure, so we can simply add them or concatenate them like this. X is 0, so along the rows. And then we can reset the index, so we don't have a mixer, let's say, of indices. So we drop the existing ones and replace it with the new ones directly in this command. And then we can drop some information. We will use the bus classification and also some more common, I call it main groups or common groups. So I'm sorry, Tolan class, we will remove the Tolan classification. This unknown, again, try it out. So you see there are some confusions today in this video, but I hope you can forgive me. And then we make an in place true. So we remove these columns, we drop them. And then just in case, we drop also some NA values because I think there are also some gaps in the data and we do not want to have no data with no bus classification values. So let's put it here and then in place true. Let's have a look at the asteroids df. And there we are. We have the name, the bus class, designation number, and the file path. Perfect. The final steps are now. So what do we want to do now? We have now the file path. So what's the matter? I would suggest let's load the data as well. So we create a new column. We call it spectrum data frame. And this is what I like about pandas and so on. You can be extremely flexible on how you store data in there. So let me show you something. We are creating a new column called spectrum df. We are reading the file paths. And what we are doing, we are actually reading in this data, and in each cell for each asteroid and classification, we are putting this data frame itself in there. So what does it mean? We will see in a moment. You may remember we have two columns in the spectra files. The first column is the wavelength and micrometers, and the other one is the reflectance normalized with 550 nanometers. So let's keep it like this. Also again here, just doing quick and dirty, some reset index. And maybe this, I think, no, I already did it, right? I don't need to reset the index again. Yeah, it's not necessary, but what I want to do is the designation number. That is a mixture of numbers and strings. I would like to convert everything to strings and also keep the column. Asteroids df, designation number, S type, string. Let's take a look. This may take some time. And then afterwards, we can store our final data frame. This takes now a few seconds. Okay, I'm back now. And as you can see, the loading of the spectra took only 4 seconds. So I had to rerun the entire runtime and rerun the whole script. And now it took only 4 seconds. So yeah, this can happen. That runtime sometimes crash also. So be a little bit suspicious when this command takes more than a minute or so, because the files are really, really small, and Colab is also built to handle a huge amount of data. So let's take a look at the Asteroid DF file we just created. We have the name, we have the bus class, we have the designation number, we have the file path and the corresponding spectrum DF. Now the spectrum DF here, it's quite interesting because let's take a look at the very first cell of the first cell here in this first row. And this cell here is itself a data frame, a pandas data frame with the wavelength and the reflectance. So the reflectance spectrum, which is quite nice, I would say. So what we can do now is we can store this file in Google Drive again, so we don't have to redo this whole process. So let's use pathlab path, os path, join core path, and then let's say we store this in level 1. So our first derived data set, we create the directory, and of course if it exists, then okay. And now we can store the Asteroids DF. We will use this pickle format and then store it here. So we don't need any fancy file format like a data lake, delta lake whatsoever, because these are quite small files. So let's stick with simple solution. So let's call it asteroids merged.pkl, asteroids pkl, and that's basically it. I think there's also some, I think this, let's get it running. I think I did the same mistake already once. Yeah, and that's basically it. So we are finished now. The file is now stored. So let's take a look here, level 1. And there is the file. And the file, I think, is not that. No. I want to take a look at the details. Ah, there it are. 1.5 megabytes. So this is really, really small. So it's not really big data or whatsoever. But this is not about big data. It's about the machine learning thing. And we don't need huge amount of data to work on a nice machine learning topic. The script here with some more details will be uploaded on GitHub. There will also be a batch where you can simply click open in Colab. You can simply run it and or follow it with the tutorial given here, or just simply go through the comments as you like. Next time we will do some more data parsing. We will understand a little bit more the relations between the different classes, Tolen, bus, and so on. Enrich the data a little bit. I want to throw in also some more science videos also about asteroids and spectra and so on, because I think this is a very interesting topic. And we will work with spectra a lot in the future, not only with asteroid spectra, but we will also work, and I promise, with big data using spacecraft instrument data. But first, let's stick with the asteroids data. Let's see if you can handle also here the script as me today. There was some confusion sometimes, but this things happens. Now you can imagine how it is sometimes to work on a use case where you have nothing prepared. It's even more confusing sometimes. Of course, Jupyter Notebook, it's quite difficult to test things always, so you have to be really careful. If you just use Python scripts or want to write a library, always use and apply unit tests. Really, it will save you. It will save your nights. You will not get any nightmares of non-working code. But in our case, everything remains quite simple and easy. So I would suggest let's call it a day. Let's keep continuing next week. And until then, happy coding, enjoy the scripts, and see you next time.